So is there anything you want me to go over from the last class before we proceed with the remainder of lecture 9.1 and then on to lecture 9.2? It assumes you know everything about forecasting and you know everything about heuristics and you know everything about inventory management. Okay, so let's continue to problem C. So if you recall, we are doing the example which has an annual demand of 7,300. All the other inputs are given. We want to achieve a probability of not stocking out 95%, a fill rate of 98%. So we saw that the current policy where they are ordering at reorder point 250 and order quantity of 500 is achieving a probability of not stocking out of 90.3%. So we've done all those problems. We've checked what the fill rate is. We've checked what the probability of not stocking out is. So today we're going to complete this and look at what is the reorder point, what is the S that we need to set to achieve a PNS target of 95%, and then calculate what the safety stock cost is for that PNS target. So the first thing we have to do to calculate a PNS, can anybody get us started? What's the first thing that we have to do? How do we calculate the other point? Who wants to get us started? Yes? Anybody? How do we calculate reorder point? S is equal to average lead time demand plus K times standard deviation of lead time demand, right? Yes? So what is K? Sorry? 1.3? Hold on a second. Can I hear you better now? Yeah. For the new reorder point, what is K going to be? Because the first time we got K from the reorder point that they were using, right? So now we have a new reorder point, so how do we calculate K for the new reorder point? Yeah, so K is the inverse CDF of the standardized lead time demand distribution, right? Yeah? So, K is the inverse of our So again, going back to that graph I showed you, we want to see what is this K when we have 95%. So this is 95% of the area under the standardized normal distribution, right? So we want to find out what that K is. So how do we do that? We go back to our table 1. So if you go into your notes and you pull out table 1 at the end of your notes, you will see that that's a table for your inverse CDF of the standardized normal. So along the left-hand side, you'll see the rows is the first decimal place, and along the top, you'll see the second decimal place. So our target is 95%. So in probability terms, you read it as 0.95. So along the left-hand side column, you see 0.9, and then you go along that row to see where you find the column for 0.05. Okay, because that will be the reading. So what do you get?
1.645.
So that will be 1.645. So just for completion, I'm going to write this down as, whoop, keep getting the wrong pen. So I'll write this down as the inverse CDF, and our probability of not stocking out is 0.95, and this works out to be 1.645. So we know from the inputs that are given to us that our mu x is equal to 200. We know that our standard deviation that we calculated was 61.319. Everybody with me so far? Yeah? Okay? So we've already calculated mu x is given to us. We already calculated sigma x. So we just plug this into the formula. And we always round it out to a whole number because, again, this is an inventory number. So we round it out to 301. So this says that we round up 301. So what's our calculation for safety stock? How do we calculate our safety stock? Yeah, exactly. So we have safety stock is equal to S minus the average lead time demand, which is 301 minus 200, which gives us 101. And our safety stock cost is equal to safety stock times the value times the holding cost, which is 101 times $75 times 30%, which gives us a total of 2,272 and 50 cents. So, in other words, if a company is using a certain policy, using some sort of arbitrary reorder point or order quantity, you can go in and calculate what is their realized customer service level for the probability of not stocking out, or the P1 customer service metric. You can calculate the P2, which is the fill rate metric, and you can also see if there is a target customer service metric, whether those metrics are aligned or not. Most likely, if somebody does not know how to calculate inventory, they're not going to be aligned unless it's by chance, which is a very small chance. So you can also go in and you can look at what the company's targeted customer service values are, their metrics are, and you can calculate the reorder point in order to achieve that. Okay? And then you can calculate all the other costs associated with it. Any questions about this?
So when they get 301 units, that's when they enter the reorder.
Yes. So when the inventory position either reaches 301 or passes 301, then you want to place an order. So that's the trigger point. Okay? Is that clear? Okay. Let's move on to looking at some Excel models now. I'll first explain these to you and talk about some extensions, and then we'll look at them in Excel. So, this is the P1 control that we just solved. When you do a P1 control, then if you're going to solve it without a non-linear program, and we'll be looking at some non-linear programs, then you're often going to set your Q as your EOQ, which you're familiar with. Okay? Now, Ty and others who have not taken the 355, you won't know EOQ, but it's a relatively easy concept to pick up. Your reorder point is going to be the inverse CDF of whatever your P1, that is your probability of not stocking out, target is. Right? We just did that. Now, you could also set in Excel your S relatively simply using an Excel function. This Excel function is taking the inverse CDF of the lead time demand distribution directly. So you don't have to convert it to the standard distribution. So all you're doing is taking the inverse of the distribution of the lead time demand, for which you're entering the parameters of the average lead time demand and the standard deviation of lead time demand. So you still have to calculate those two. Okay? And then you're asking the Excel function to return at this probability of not stocking out, or at this percentage underneath the normal distribution, to return what that value is going to be, what that X value is going to be. Okay, and that's your reorder point. Now, your estimated total annual cost, given this, so there seems to be some confusion, and this might be because you all might not have the foundation classes, but this is basically a representation of a function. So whenever you see something that is in brackets, those are inputs into a function. Okay? Those are variables. So S and Q are variables that are inputs into a function. And the name of the function is usually given on the outside. Okay? So the function for estimated total annual cost is a sum of all of these costs. And of course, Q is an input into order cost, Q is an input into cycle service, the cycle stock cost, and S is an input into the safety stock cost. So this is when you calculate it by hand. The next one is the P2 control, or the fill rate control. FR stands for fill rate. And here, we're going to solve this as a non-linear program. Okay? And we'll see in a minute why. So, a non-linear program which has two decision variables. Again, going back to the foundation, the basics of mathematical programming, we start with the decision variables. And the decision that the managers have to make, remember what we said, what's the basic decision of inventory management, is you have to know when to order and how much to order, right? That's the decision. The objective is you're trying to minimize cost. So that's your minimum. You're trying to minimize your estimated total annual cost. This is, and again, this going back to 355, this is your ordering cost. And I gave you these values in the last lecture as well. This is your cycle stock. And this is your safety stock. And then this is the dollar value to convert those into cost. And right here, you have your pipeline stock cost. So really, the main part of the function where you have the decision variables actually influencing the outcome is right here. So you have Q there, and S right there. Okay? So this is usually a scalar value, and this does not influence the outcome, your pipeline stock cost. Now, we have to set some restrictions on the variables. So the first restriction is your reorder point has to be more than your average lead time demand. Remember what I talked about last class? That the critical risk period is from when the order has been placed until when the order has been received, right? Because during that time, you really don't have any orders that are arriving in order to satisfy any demand that might be in excess, right? So that reorder point must be sufficiently high to cover all your lead time demand, which is your mu x. And of course, yes, you have a question?
Yeah, I just wrote it all out and I'm erasing that yet. What is like CS, SS? What does all that mean? That you wrote out?
This is cycle stock. Okay? So the average on-hand inventory. This is safety stock. Okay? And PSC is your pipeline stock. So pipeline stock cost. So your reorder point has to be more than your lead time demand. You always have to order more than one unit. All right? So that's your variable restriction for S and Q. We have to constrain the system in order to ensure that we meet our fill rate. So for that we have two functions, our expected shots per cycle and our target shots per cycle. Let's start with our target shots per cycle because that's the easier one. So our target shots per cycle is, we say we want to have a fill rate of 90%. All right? So that's our 90% fill rate. So 1 minus 90% is 10%, right? So each order Q, we want to make sure that we only are short by 10% of Q. All right? So that's our target shots per cycle. Does that make sense?
Target.
Shots per cycle. So that is how much of demand we want to be short by each cycle. So we cannot fulfill that much of demand in each ordering cycle. Okay? So we're just taking the fill rate and converting it into a number of units by which we are short of fulfilling demand each cycle. Okay? So that's our target shots per cycle. We're saying we don't want to fulfill more, we don't want to fulfill less than this amount of shots per cycle. Okay, so we have a 90% fill rate. Of that, say we have an order quantity of 100. We want to have only 10 unit shots per cycle, no more than that. Okay, that's our target unit shots. Our expected shots per cycle. Now this function over here is that complex function I was talking about, which is the normal loss function. You remember the GZ function I was talking about last time? Or, the GK function? So this is your GK function. And you can see that K is the input to that function. And this is called the normal loss function. I'll just write it out somewhere else. So this is your GK or normal loss function. And now you can see why it's a nonlinear function. Because K is our P2 control, and K is going to be the input into our expected shots per cycle, where we're going to force expected shots per cycle to be less than our target. So we're not going to have any more than, in our simple example, 10 units short each cycle. Okay? So the maximum number of units we are going to be short by is 10 units in each order cycle. And that's what this constraint is doing, this third constraint. So what we have is our expected shots per cycle is calculated by our normal loss function multiplied by our standard deviation of lead time demand. Okay? So that's just theory. That's just how it works out. Yes?
Normal.
This one here? Normal loss function. Normal for the normal distribution. So, this normal loss function can be easily written out in Excel using this function over here, where we have the normal distribution of K, which is the standardized value of the FR, and then you have to use, in this case, not the CDF, but the PMF, the probability mass function. So you use a false because it's not a cumulative distribution, minus K times the standard normal distribution, and this time it is a CDF, which is indicated by the capital F. Okay? And that's how you enter this nonlinear program into Excel. And I'll show you an example after we've gone through all of the other problems as well. The next problem is where we have a B1 control, and this time we have an unconstrained nonlinear program. Okay? Unconstrained because we don't have any constraints. We only have variable restrictions, as we had before, but we don't have any constraints because now we are including the customer service criterion into the cost function, into the objective function. So what we are using over here is we are using B1, which, if you recall, B1 is the customer service criterion, which is a cost per stock out. So every time you stock out, you incur a cost. Okay? So here what we have is, whatever our probability of not stocking out is, we have the number of orders that we have times that multiplied by our B1. And that will give us our S and our Q values using the nonlinear program. And we get P1, and again you can see why it's a nonlinear function, because it is, our P1 is equal to S minus mu x over sigma x, and you take the standardized normal distribution of that. So in other words, you're converting that into a K value. All right? Which, this is just a standardized version of the reorder point, which is really K. So in this case, all we're doing is we're saying, okay, we're including the cost of stocking out in our objective function. So as a result, whatever our total cost is, we are trying to minimize that, including minimizing the number of stockouts that we have and the cost incurred by that. So that, because of that reason, we don't actually have to use any constraints. And in the final problem, again, this is unconstrained. This time, for every single unit that we are stocking out, we incur a cost. So this time, instead of multiplying by the number of stockouts, this is the number of times we expect, or the amount of units we expect to stock out by. Okay, so that's the expected shots per cycle, times the number of cycles that we have, which is the total demand divided by Q, multiplied by B2. And again, we have the same formulas for calculating expected shots per cycle, which again is using our S implied as a K. Okay? Question? Okay. So that's basically the B1, the B2, P1, and P2 controls, and we can calculate them in a spreadsheet rather simply, and I've given you that spreadsheet we'll look at in a few minutes. But before we go to that, I wanted to explain a couple of things. So far, we are assuming that the lead time demand is normal, as I've showed you. I've given you that one of the problems with normal lead time one of the problems with the normal distribution is that the normal distribution goes to negative infinity. So there's a likelihood that you will get negative demand, right? Negative lead time demand, which is not really a possibility. So as a result, the researchers have looked at this and said, it will be better to model this as a gamma distribution. And a gamma distribution has a very appealing property where it does not go beyond zero. Okay, the distribution starts at zero and then goes to positive infinity, which is an appealing property to have to model lead time demand. So what we have over here is a gamma distribution with two inputs, two parameters, alpha and beta. And alpha and beta can be easily approximated from the mean and the standard deviation of lead time demand. So all we have to do is we take alpha, or we take the square of mean, the square of the mean of lead time demand, divide by the variance of lead time demand, and that gives us the alpha parameter. And then we take the variance of lead time demand and divide by the mean of lead time demand, and that gives us our beta parameter. Now once we have an alpha and beta parameter, it's relatively simple to just make the modifications of what P1 is, P2 is, B1 and B2 is, using just the simple Excel functions that are available built into Excel. So, for example, to calculate the P1 criterion, you just set the reorder point is equal to the gamma function, where you have the same P1, but instead of the mean and standard deviation, now you're using alpha and beta. To calculate the expected shorts per cycle, instead of using the normal functions, now you're using a gamma function. Copying it exactly as this is, alpha plus 1 beta true, and then s times 1 minus. So here you don't use k, you're using s. Because remember, k is from the standard normal distribution. So here you're entering s directly. So in a way, it's a lot easier to write out these formulas for the gamma distribution as well. For the B1 criterion, all you're doing is you're setting the 1 minus P1 as 1 minus this gamma function. And then for the B2 criterion, all you're doing is you're changing the expected shorts per cycle to this formula. And then you have the gamma distribution where you're calculating all of these expected total annual costs, and you're calculating the reorder point and the order quantity based upon the gamma distribution, so the normal distribution. Okay, so let's take a look at modeling these in Excel. So here is the same data that we have used in our formulas, and we're going to now put this into an Excel sheet where you have each of these examples that I gave you. So this one is the P1 control, and I've got both the normal as well as the gamma here. So, you have the decision variables over here, so I'm only going to focus on the normal and the gamma is on this side. So you have the reorder point, which is calculated using the normal inverse value of the average and the standard deviation of lead time, which is calculated on the previous sheet. And then the Q value is calculated using the EOQ. And then from that, you can calculate all these other values. Okay, so that's just a standard manual calculation that you would do. For example, when you first wanted to check what the reorder point might be manually. The next one is where you're looking at the P2 control. And here we have our fill rate or our P2 control. This is a decision variable S and Q, so there is no formulas over there. And here we have our formula for expected shots per cycle. That's the same formula that we put in, that I showed you in the notes. And then the formula for target shots per cycle, which is a function of Q. And then here's your total annual cost. And then to enter the nonlinear program, it's the same way as you would do for a linear program, except there's one difference. So here we have the objective, which I've named the cell ETSC. I want to minimize it. I have my changing cells, which are S and Q. So I have Q is greater than or equal to 1. I have expected shots per cycle are greater than or equal to the target shots per cycle. And I also have my S is greater than or equal to my lead time demand. The only thing that I have to do different is now I don't have to make unconstrained variables non-negative, because my S and Q are the only variables, and both of them are constrained. One to greater than 1, and the other one to greater than average lead time demand. So I can either check that or leave that unchecked. It doesn't matter. The only thing I have to make sure is now, instead of a simplex algorithm, I have to use the GRG nonlinear algorithm. That's the only thing. And then when I solve it, I can get the answer to the problem. And here the B1 control is the same way. So here I have my expected total annual cost and my safety stock cost, which is dependent upon my safety stock, and then the safety stock is going to be dependent upon my reorder point. So the realized service level that I have is given by the norm, the S, this is D12, so the S minus mu x over sigma x, which is just your standardized reorder point. And my set service level is the 95%. So I put in the solver the same way. And this time, remember, it's unconstrained, so all I'm doing is I'm restricting the variables. I have the expected total annual cost, I have the minimize function, I have the changing variable cells, and then so that's the gamma function that I'd set it up to. Let me do the normal now. So here what I've done is I've saved the solver values. So now I've got the gamma values that are set up, so I'm going to change it. I'm going to load the normal values. Oops. So it asks me to replace, and then it's replaced the normal column values into the solver function. So now I can go in and solve for so now we have a total annual cost of 10,284. My safety stock cost is 1,843. I can see that my realized service level is close to 95%, which is what I want. And so this is the unconstrained, because now what I have is you'll see that in my total annual cost, I have included here what is my stock out cost. Okay? So that stock out cost is part of the objective function, and as a result, the objective function is not going to be too much, and it's not going to allow too many stock outs because that's going to increase the objective function. And the objective function is this. This is the shots per cycle times my B1 criterion, which is given on the first inputs page. So that's the B1 criterion, and this is the B2 criterion. The only difference is we are now using, let's do the B1 criterion. So now we are only doing, for each unit that is short, we are multiplied by a certain number or certain penalty cost. And that penalty cost is calculated over here. So I expected shots per cycle times how much it costs to stock out each unit, multiplied by the value, multiplied by the number of orders per year, and you do the same thing. Okay? So that's really it for the first part of inventory management. Is there any questions about this? Yes?
Like, to what extent will we be able to will we have to make one of these for the exam?
For the exam, no. But we don't have the courses as yet because you are still in the area of emphasis. But certainly, if y'all come back, y'all will need it. If y'all want to do the major, y'all will need to do it because y'all will be using it in future courses where we actually do production control and we actually do network analysis and stuff like that.
So I guess what I'm really asking is how we use this.
I don't really care about the tests. I mean, I've said this to you all privately, individually. For me, I really don't care about tests. I don't care about grades. I don't care about, student evaluation, instruction, all this kind of stuff. That doesn't bother me at all. What bothers me is what you'll learn. So, for me, my question to you is, what do you want to learn from this? Do you want to learn anything from this? I'll be happy to go into more depth. But it's entirely up to you, all right? Because this kind of stuff is invaluable. There are four courses, there are 4 programs in the country that teach, 4 programs in the world probably that teach this stuff, all right? And I've been at 3 of those programs. So my point is that you all can learn as much as you want from this or as little as you want from this. It's entirely up to you, okay? This is for you to develop your careers, all right? Any other questions? And I said, I'll be happy to go into whatever depth. That's why if you saw the syllabus, I have one entire lecture period that is free to go into depth into whatever you want to go into, right? So whatever you see fit, whatever you think you will need in your job. I know that quite a few of you already accepted job offers, so you have a good idea what you want to do. So I'll be happy to go into whatever depth you want to go into for these, models. Yes?
What are those 4 programs?
Sorry?
What are those 4 institutions?
Ohio State, Penn State, Michigan State, and now we. So, any other questions?
Will our jobs expect us to know a lot of this coming into that?
No, my experience is that your managers and your supervisors, even up to the chief supply chain officer, has very little knowledge about this because we've been teaching this in the graduate program for the last 35 years. The textbook on this is written, last edition was written in 1997, okay? And it's being taught in the actually I can say with safety that Michigan State doesn't teach this. They stopped teaching this about 15 years ago. So I've got 3 of my PhD students are there and I know they don't teach it. And to answer your question, it's more than likely that your manager, your supervisor doesn't understand this stuff. What I think it's really valuable for is by making yourself visible and useful in an organization, by showing how you actually understand. A lot of this stuff is not actually useful for implementing directly, but providing really good insights into the type of decisions that need to be made, right? And as I'll be talking about today, this is one part, just like forecasting. Getting a forecast is one part in the total demand management process, okay? Because I understand the forecast of one item, but I have 3,000 items to manage, all right? How do I do that effectively? Okay, I understand what my demand for one item is. Now I can understand what my demand for 3,000 items are, and then I can manage by exception. One item demand has gone up. How do I know that? So in fact, if you want, I've got data of a company. For that one lecture, I can actually show you a lot of other techniques, data visualization techniques, ABC analyses. I can show you for large data sets using a very small toy data set. I mean, this is only 15 megabytes. The data sets that you'll be working with are, your companies collect, Walmart collects about 5 petabytes of data every hour at every store, okay? And to give you an example of the scale, if you take every single piece of information in the Library of Congress and put it together, that's 20 petabytes of data, right? I'm talking about digital as well as written, right? So imagine the Library of Congress, 20 petabytes. Walmart alone collects 5 petabyte data an hour, okay? Google collects that in 5 seconds. So the point is that a lot of this stuff is extremely useful. It's entirely up to you what you want to learn from it or not. Okay? So, I'm off my soapbox now. Right? So, any other questions? Or if you want, you can think about it, and we can certainly go over it again in that one lecture period that I've kept waiting. Right? All right, let's go to the next part, which is distribution resource planning. So we talked at length about how do we model, but what we're really doing is we're modeling just one item. We're modeling one item in one location, and we're doing it in a very, very restrictive way. So the reality of any supply chain is it's multi-echelon. Everybody know what multi-echelon means? That means it involves multiple stages in the supply chain. A supplier, a producer, a wholesaler, a distributor, a retailer. So at every echelon of the supply chain, even if you have a single company, you could have a central distribution center, you could have a regional distribution center, and then you could have retailers, your retail firms. Now, in order to manage inventory in a multi-echelon network, we have a heuristic we call distribution resource planning, which works very similar to a materials requirements plan, an MRP. So, you have a plant, you have regional distribution centers, and then you have retailers. There's inventory all across that system. The problem with using an SQ system or a continuous review system, or 2-bit continuous review system for a multi-echelon is you're ordering in fixed order quantities. And if you allow each echelon and each facility at each echelon to manage their queue independently of the entire system, then you are going to have a lot of noise in the system, and you're going to have amplification of demand in the system. Now, we saw that with a very simple example last term, right? Last semester. We saw that with the beer game. We all played the beer game, right? So we saw how just by not coordinating our efforts, by not coordinating how much we were ordering and not seeing what the demand was, you could create that amplification. Something very similar happens over here. So our queue is a lumpy demand, right? In other words, we're not ordering as the demand is happening. We are waiting and then we're ordering after some time, right? That's the whole point of the reorder point. So what can happen is, in a real world system, if you are incentivizing managers on how you're serving your customers and how you're fulfilling customers' demand, then there's going to be some sort of gameplay that's going to happen in the supply chain. you're going to have managers that are going to order more than they need, and they're going to hoard that stock, which means that as you go up the supply chain, the plant is going to see unrealistic demand, right? And we've experienced that in the bullwhip effect, in the beer game. You're also going to see other areas of the supply chain stocking out because the plant has finite capacity. So what can eventually happen is the plant will have unrealistically high safety stocks. Other areas in the supply chain are going to have unrealistically high safety stocks because they have to deal with the variability of the lead time coming in from the plant. Sometimes it might be there when they expect it or before they expect it. Sometimes it might take more than a month for them to get it. So now, based upon that, you can see how your safety stock is going to change, right? So that's the problem with using the SQ system. So here's sort of just a representation of this problem. So we're all familiar with this. We saw this in the beer game. Retailer customer demand is almost flat. Remember that? And then we have inventory at the regional distribution center where you're evaluating inventory. It's hitting the rear point and you're placing an order. And that gets amplified as it goes up in the ordering patterns, and the ordering patterns might be different. And then what you see at the plant is a completely random, noisy demand that is very, very different from what the actual customer demand is. So, the lesson that we learn is layers of demand or layers of inventory create lumpy demand.
Okay, do you know what page of the notes
This is a completely new set of notes.
I figured, I am.
Page 2.
It's on.
It's a whole new lecture. It's not in the 9.1 minutes.
It's 9.2.
Oh, I thought we. Okay.
Yeah.
Sometimes 9.1 and
Yeah, like.
0.1, 0.2 minutes were together. Other than like that.
This one should be 9.2 though, because I got it lecture. It's lecture 9.2, I believe. Yep.
Yeah.
So is there confusion about the notes? Does everybody have this note?
It's just usually like when you do 9.1 or like 8, whatever, it's
Mhm.
like you finish out the packet before you move on to this next one.
Ah, that is for the demand forecasting, yeah. So I'm still in the process of writing a book, and depending upon how the chapters are developing, yeah. So that's the reason why. I'm sorry. It's the different chapters are shaping up differently. So this is breaking out into its own chapter. The demand is going to one chapter. So yeah, sorry. Partly that's the legacy of the numbering that is going on. All right. So this is the result that you've seen already in the bullwhip effect. So we have something called the distribution requirements plan, which is a heuristic of sorts. And what we're doing is, so just think about this before you write this down. What we're trying to do is we're trying to manage multiple stock keeping units. And what do we have to manage in multiple stock keeping units? Basically, we want to know when they can order them and in what quantity should we order them. So the DRP looks at all of the ordering patterns across all of the different SKUs and then says, how can we combine the ordering pattern for different SKUs in order to improve or smooth the ordering process? So that's why it's known as what's called a time phase order planning system, where you're looking at how can we smooth out the ordering over time in order to improve our efficiencies at different points of the supply chain, while also trying to keep the essence of the inventory policies or keep to the essence of the inventory policies for each individual item. So let's look at what we need to calculate a DRP. So to calculate a DRP, we start with a table that we construct for each SKU. So for each SKU, we collect some information, okay? And we collect the location of that SKU, where it's being stocked, where it's produced. We collect information on how it's being transported, what carrier, what is the lead time. And then we look at the starting balance on hand. How much do we have right now in the DC? Then we look at what inventory controls we have for that SKU. When do we order? How much do we order? And then we say, okay, what is the planning period that we want to look at? What are the forecasts? And do we have any orders already scheduled? And when are we going to receive those orders? And then we look at what are the actual shipments that have been already shipped for that SKU. And when we look at this in an actual example, it becomes a lot more clearer. So that's basically what we want to see. We want to see information about the SKU, where it is managed, what is the inventory policies, and what are some of the operating parameters that are currently in place. So, while we're doing the DRP calculation, we need to know when to order, how much to order. We also need to keep track of the safety stock. And we want to compare what is the balance on hand and what is going to be received to a certain reordering criterion that we're going to calculate. So we have to decide for each DRP, for all of the SKUs that we're going to manage, we want to determine a planning horizon. Now, you're familiar with that from forecasting, right? What is the forecast horizon? Now, this is different. A planning horizon is we're going to look at a certain period out, and our DRP is going to look at a time phase for all of the orders during that period. And it depends upon each industry. For example, they might do it by season. For one season, they might have one planning period. For another season, they might have a different planning period. And if demand is stationary more or less throughout the year, then they might just divide the planning periods into equal portions related to probably the production capacity of the plant. Okay, so again, the planning horizon can change drastically. The reorder, we look at this in the example, but what we have to do is we have to calculate the reorder criterion, which we are going to call Z. So the reorder criterion will help us understand when an order is triggered. And when you work this out backwards, this is nothing but your reorder point, okay? Because it includes your lead time demand, it includes your inventory position, and it also includes your balance on hand and your inventory position, which is equivalent to your reorder point. So, how do we evaluate? When our Z is less than our safety stock, then what we do is we have a planned order release, or POR. In other words, at this point, based upon this forecast, given our starting balance on hand, given our lead time, and how much lead time demand we expect, that is going to be a period when we are going to release an order to either the DC or to the plant. And then at the end of the planning horizon, in a particular table, we look at what is the total number of planned order releases, and then we compare it to all of the other SKUs and see all of the planned order releases, and then calculate a total planned order release from a DC going to a plant, or we calculate at the plant, how many planned order releases are coming for one SKU from all of my DCs. And again, we'll do an example and that'll become clearer. So let's go and start doing examples, and these things will become clear. So here we have one SKU, which is the beef noodle soup, and it's located at the Columbus Distribution Center. We've calculated an order quantity of 3,700 units, a safety stock of so much, and our carrier gives us a lead time of 2 days. And this is coming from central Pennsylvania. It's coming from, I forget the name of the city, but somewhere in Center County, Pennsylvania. And we start with a balance on hand in the current period of 5,925 units in the Columbus DC. We have a planning horizon of 9 periods. For some reason, this has not come all together. It's not come here. So we have a planning horizon of 9 periods, and then we have our forecast for those 9 periods. Okay? Is that clear so far? All right. So the first thing that we have to do is, based upon our current balance on hand, we have to calculate the balance on hand of the next period. So we go and check and see, are there any scheduled receipts? Are there any shipments on order? We say there are no shipments on order, so we put in 0 as our scheduled receipts. Oop, wrong color. All right? And then our ending balance on hand minus our forecast gives us our balance on hand for our next period. So, what is our Z now? Our Z is our balance on hand plus any scheduled receipts that we're getting minus our lead time demand. So our lead time demand is 2 days. So in other words, if our lead time demand is 2 days, or our lead time is 2 days, that means we'll get any orders that are placed in 2 days, right? So we want to make sure that if the order is coming in the third period, because the lead time is 2 days, then we want to make sure that we cover enough of demand for those 2 days. So we look at our forecast that is for those 2 days. So we add up. So we know that there's no scheduled receipts in this period, so we have to add up these two values. And from that, we have to subtract these two values. And when you go back to this formula, that's exactly what it's doing. It's balance on hand plus the sum of scheduled receipts in the future periods minus the sum of forecast during your lead time. So that value works out to be 1,145. Now we know that we place an order when Z is less than or equal to our safety stock. Okay? So since Z is less than or equal to our safety stock, then we place a planned order release. And then I'll put this in a different color. So we have 3,700 units. We have 3,700 units that are in transit in this period, and then they are received in this period. Because our lead time is 2 periods, so place an order, first period, arrives in the second period. Now, we do the same thing. This is our balance on hand ending of this period. And then we calculate, we have to add any scheduled receipts. Those are 0. And subtract it from 1460, which gives us our new balance on hand, which gives us 3,005. So to calculate our z value, again, we do the same thing. We add up these two values, and then we subtract these two values. And then that gives us 2,445. So this is greater than that, so we don't have any planned auto release during that period. We do the same calculation for the balance on hand. We add up this value and this value, and we subtract this value. And then that gives us a balance in hand of 4,485. So there's no orders coming in the next period. We know that because our lead time is more than 1 day. So to calculate our z value, we add up these two values and we subtract these two values. And that gives us a z value of 45. So clearly 45 is less than our safety stock. So we have a planned order release, which I'll put in a different color. We have in transit on this period 4, and then we receive it in period 5. So that's how we constantly update our DRP. It's just a matter of going through and just following through and then following the formulas and just doing the same thing over and over again for the entire planning. All right, yes?
4,485 minus 48,000.
48,000 or it's 4,800?
Yeah, 4,800 still.
Right.
4,800 is bigger than 4,400. So that'll be a negative number.
Sorry, this calculation was wrong here. This should be 4,845. Yeah. So this should be 4,845 because you have 3,005 plus 3,700, so that's 6,705 minus 1,860, so we do 4,800.
How did you get that number again?
How did I get this number?
Z, BOH, and...
How did I get 45?
Yeah.
Okay.
No, that one.
484.5?
Yeah.
Okay. So I took 3,005 plus the scheduled receipts, 3,700. So my balance on hand
Yeah.
plus whatever I'm getting in receipts minus my forecast demand will give me my balance on hand at the end of that period. Okay? So you just basically continue updating the table in the same way, and you're going to get the entire DRP table. So this then works out to be 2,445, and then you get 745 here. So 745 is less than safety stock, so I release an order. It's in transit here. I receive it in this period 6. And so my balance in hand for period 5 will be 3,745. My Z value is 1,445. So I have a planned order release which I receive in period 7. So now my balance on hand will be 6,745 minus 3,700, which is 4,445. Oops. That's why it's useful to have computers do this for you. And you can very simply set this up in a computer. And then my Z value works out to be in 1945, which I have to release another order. Which I receive in period 8. So now I go back and calculate my balance on hand. Oops. I keep putting the So now my Z value is 4,185, which is more than my safety stock, so I don't have to worry about placing any orders in that period. And no orders placed in period 8 either, so this is 1460, and no planned order releases. And that's the end of my planning horizon. That's how much balance on hand I have at the end of the planning horizon. So this is a DRP for one SKU. Now you have to construct a DRP for all of your hundreds or thousands of SKUs. All right? So what you would do is you would take this and put it in an Excel sheet and do it for all of your SKUs. Yes?
Yeah, no, you don't care about tests, like you said before, but like, do you have to do this on the next test for an SKU?
Sure. You could, if you would. It might be on the homework as well, on the next homework, likely. So, the DRP example, a full DRP example is where you would have the DRP table for every single SKU, and every single SKU would then have a planned order release. And then we would put that entire planned order release together for all of the SKUs, and we would see how much for that particular distribution center. For Columbus distribution center, we'd look at beef noodle soup, we'd look at chicken noodle soup, we'd look at beef stock, we'd look at chicken stock, vegetable soup, and all of those different SKUs, and see how many orders are we releasing during each one of those periods. And then we would say, okay, for each week of January, for each of February, this is how many orders we're getting, and this is how many orders we're going to be receiving. Okay? And just keep that in mind, because that's going to lead us to some interesting insights. So, we're going to see how DRP is used for coordinating replenishment, how it's used for combining orders to realize some economies of scale in transportation, and also for helping schedule your labor, and finally to develop a master production schedule. So, as I said, we look at producing DRP tables for every single SKU, and then we will look at how we can lock those orders in. So let's take a look at an example as I was describing for the entire distribution center. So here we have DRP tables for every single SKU, every single soup item in this DC. Okay? I now recall the production facility, Center Hall, Pennsylvania. So the production facility that supplies all of this soup comes from Center Hall, Pennsylvania. And this DC is placing its orders with that plant. From the DC perspective, we're looking at all the planned order releases and we're looking at all the scheduled receipts. So for each period, we're adding up the scheduled receipts. So here is 0, 0, 0. So there is no scheduled receipts for the first period. For the second period, we have 5,700, 7,100, etc. So the planned order releases, we're adding them up, and at the bottom, this is the total scheduled receipts and total planned order releases for the entire distribution center for one category of items. Okay? I've graphed out the planned order releases, and if you notice, the scheduled receipts is just the planned order releases shifted by one period. Okay? Because the lead time is one for every single one of these items because they're coming from the same plant. So looking at this, what is the first thing that you realize when you look at this graph from a distribution center manager's perspective? So these are the planned order releases, but you're also going to get the same pattern for your scheduled receipts. Yes. And what do we know from Lean, Six Sigma, from managing a lean operation? Is variation is bad, right? So this, if we were to order, so this sort of gives you a microcosmic view of what happens when you use an SQ ordering system. All right? An SQ ordering system creates uncertainty at all levels. So if there's uncertainty over here, you can imagine what the plant is receiving from all of the distribution centers that it's getting. But from a distribution center perspective, you can see from a scheduling perspective and from a transportation perspective, sometimes you're getting less than truckloads, sometimes you're getting 1.5 truckloads, sometimes you're getting, maybe you might get a truckload. All right? So now you have the opportunity of combining orders in order to achieve transportation economies. That's one. The second thing is I can change those in order to balance my labor requirements, because sometimes I'm going to have people just hanging around doing nothing. On other days, I'm going to have people running around helter-skelter, probably working overtime, right? So from a distribution center manager's perspective, this helps me to understand, okay, now maybe I should move some of these orders and put them somewhere else, right? And then go back and then see. And that's what the DRP heuristic allows you to do. Okay. Now, looking at it from a plant perspective, so this is the MPS for the Center Hall facility. So our plant is in Center Hall, and here we are looking at a master production schedule based upon the planned order releases coming from all of our plants for one SKU. So here again, clearly you can see the problem. Yeah? So now we can work with our plants and we can say, hey, instead of ordering in this period, can you place an order a little bit earlier? And then from a transportation perspective also, can we smooth out this ordering pattern in order to realize some economies of scale by ordering in full truckloads and making sure that we're still fulfilling our customer demand. All right? So let's stop here and we'll continue with the rest of this lecture. And then just a reminder, 9.3 is most likely going to be in a separate set of notes. So make sure you check that. We will start 9.3 next on Tuesday. 9.3, yes.